This is a picture, 8 pixels wide, 8 tall, but to the machine showing it to you, it is not a picture at all. It is 192 numbers. No shapes, no colors, no sunrise, just numbers. Here they are, 3 for every pixel. Right now, they probably mean nothing to you. By the end of this, you will read every one of them, starting from a single switch, and hold on to one question: why is a byte 8 bits? Start with the only thing a computer really has: a switch. It is on or it is off. There is nothing in between. No maybe, no 70%. 2 states, and that is the entire vocabulary. That single yes or no is called a bit. It is the smallest amount of information that can exist. A computer does the same thing, just smaller. A transistor is a switch with no moving parts. Current flows or current is blocked. We call one of those 1 and the other 0. A modern phone chip holds around 20 billion of them, each one flipping billions of times a second. Now, why only 2 states? Why not 10 and store a decimal digit in every wire? Because electricity is noisy, and noise moves voltages around. With 2 levels, there is an enormous gap between them. Noise cannot push a 0 far enough to look like a 1. With 10 levels, the gaps are tiny, and a little interference gives you the wrong digit. People did try. The Ceton, built at Moscow State University in 1958, was a real working computer that used 3 states. 2-1 because 2 is almost impossible to get wrong. But one switch gives you 2 possibilities, and we need 192 numbers. So we add a second switch. You already know how this works, because you already use place value every day. "407 is not the symbols 407. It is 400s, no 10s, and 7 ones. Each place is worth 10 times the place to its right. Binary does exactly this, with 2 instead of 10. So the places are 1, 2, 4, 8, each one double the last. Here are 4 switches. Every switch that is on contributes its place value, and you add them up. That is the whole rule. Watch it count. Nothing here is a code or a lookup table. It is addition, and it reaches 15 before it runs out of switches. Four switches give 16 different numbers, and every switch you add doubles that. 1 switch 2, 4 switches 16, 8 switches 256, 16 switches 65,000. "32 switches gets you past 4 billion. 64 switches gets you to 18 quintillion, enough to give every grain of sand on Earth its own number." So how many switches you group together is a choice. Computers settled on 8, and 8 is where the word byte comes from. But why 8? For the first 20 years of computing, it was not 8. It was whatever the machine's designer preferred. The IBM 704 and 7090 used 36-bit words and 6-bit characters. The PDP-8 used 12-bit words. Six bits gives 64 characters. That covers A to Z, the digits, and some punctuation, with no room at all for lowercase letters. The word byte was invented in 1956 by Werner Buchholz at IBM on a machine called Stretch. He deliberately spelled it with a Y, so nobody would misread it as bit in a memo. Then, in April 1964, IBM shipped the System 360 and standardized 8 bits across an entire product line. The rest of the industry followed. So 8 is not a law of nature. It is a decision that stuck, but it was a good one. Eight bits gives 256 codes, enough for every character anyone needed, with room spare. It is a power of 2, and it splits perfectly into 2 hex digits. Here is 1 byte, 8 ones and zeros. It is correct, and it is completely unreadable. Nobody wants to write memory addresses like that. So we fold it, take 4 bits at a time. 4 bits have 16 possible values. Give each of those 16 values a single symbol. 0 through 9 work fine, and then we run out of digits. So the last 6 borrow letters, A, B, C, D, E, and F. O is 10, F is 15. That is hexadecimal, and here is why it fits so well. A byte is 8 bits, which is exactly 2 groups of 4. So every byte is exactly 2 hex characters. 8 digits become 2, and the number has not changed at all. You have been reading hex for years without noticing. A color code in CSS is 3 bytes. A MAC address is 6. Every PNG file on Earth begins with the bytes 89, 50, 4E, 47, and those last three spell PNG in ASCII. Which raises the obvious question. A computer stores numbers, so how does it store a letter? It does not. A computer has no idea what a letter is. So in 1963, a committee simply assigned numbers. Capital A became 65. B is 66. Lowercase a is 97. The space character is 32. That is the entire mechanism. There is no deeper meaning. Somebody wrote a table, and everybody agreed to use it. It was called ASCII, 128 codes, 7 bits each, with 1 bit left over in a byte. But the numbers were not random. Look at capital A and lowercase a in binary. They differ by exactly 1 bit. That bit is worth 32, which means changing case is not a lookup, it is flipping a single switch. That is why it costs almost nothing. The digits are deliberate too. Character 0 is 48, so subtracting 48 turns a digit character into its value. And codes 0 to 31 are not letters at all. 10 is a new line, 9 is a tab, and 7 used to physically ring a bell on a teletype. Then the rest of the world arrived. 128 codes cannot hold accented letters, or Cyrillic, or Chinese, or Arabic, or Japanese. Every region invented its own table, so the same byte meant different letters in different countries. Open a file with the wrong one and you get garbage. It has a name, mojibake. Unicode fixed it by giving every character on Earth one number, about 150,000 so far. But those big numbers do not fit in 1 byte. UTF-8 solved that. Common characters take 1 byte, rarer ones take 2, 3, or 4. It was designed by Ken Thompson and Rob Pike in 1992, sketched on a diner placemat. Now the last piece. Why does a color need exactly 3 numbers? The answer is not in the computer. It is in your eye. You have 3 kinds of color receptor, only 3. Short, medium, and long wavelengths, roughly blue, green, and red. So 3 numbers is all it takes to fool you completely. A screen never reproduces sunlight. It just triggers the same 3 receptors in the same proportions. And it mixes light, not paint. Red and green light together look yellow. All 3 at full strength look white. Each channel gets 1 byte, 256 levels. 256 cubed is 16.7 million colors. Your screen is doing this right now. Every pixel is 3 tiny lights, too close together for your eye to separate. And it is expensive. A single 1920 by 1080 frame is over 2 million pixels, 6.2 megabytes raw. At 60 frames a second, that is 373 megabytes every second, which is exactly why compression had to be invented. But that is another video. So everything we need. Let us take 1 pixel, the bright one on the horizon, all the way down. Its color is 3 numbers: red 255, green 210, blue 122. In hex, that is FF-D2 7A, and underneath it is 24 switches, each one on or off. Three bytes, 24 switches, 1 dot of light. Now do that 64 times and the picture assembles itself. "64 pixels, 3 bytes each, 192 bytes, 1,536 switches. That is the number from the very first frame, and you can now read every one of them. Which leaves the question from the start: why is a byte 8 bits? Because IBM picked 8 in 1964 and everyone followed. Not physics, a decision. Check it yourself. Type printfhi, pipe it into xxd-b, and you will see 72 and 105 exactly as predicted. Next time, we wire these same switches together to do arithmetic.